Hello, everyone. In this section of electronics, we will introduce the characteristics of MOSFET devices. In the previous video, we introduced the circuit symbols of NMOS and PMOS transistors. We also introduced the operating regions of an N-MOSFET. When VGS is below VTN, no inversion channel is formed, so there is no conducting drain current. This is the cutoff region. The other two operating regions are the triode region and the saturation region. In amplifier applications, a MOSFET is usually biased in the saturation region. In digital switching applications, the device mainly uses the cutoff region and the triode region to represent the off and on states. Here we summarize the three operating regions of an N-MOSFET and their corresponding current equations. First, when VGS is less than VTN, no inversion channel is formed, so ID equals 0. This is cutoff. When VGS is greater than VTN, if VDS is less than VOV, or equivalently VGD is greater than VTN, the device operates in the triode region. The drain current is ID equals mu n C oxide W over L times the quantity, VGS minus VTN, multiplied by VDS, minus 1/2 VDS squared. When VDS is greater than VOV or VGD is less than VTN, the inversion charge near the drain is pinched off and the device enters saturation. In saturation, ID equals 1/2 mu n C oxide W over L times the square of VGS minus VTN. In the triode region, if VDS is much smaller than 2 times VOV, the current equation can be approximated as ID equals mu n C oxide W over L times VOV times VDS. Under this condition, the device behaves like an equivalent resistor RDS. The resistance RDS is the reciprocal of GDS, or VDS, divided by ID, and equals the inverse of mu n C oxide W over L times the quantity VGS minus VTN. Besides the ID versus VDS characteristic, we also look at the ID versus VGS characteristic of an N-MOSFET, as shown on the right. For a fixed VDS, when VGS is below VTN, ID is 0 and the device is in cutoff. When VGS just exceeds VTN, VOV starts from 0 and is still smaller than VDS. Therefore, VDS is greater than VOV, and the device first enters the saturation region. In this region, ID has a square law dependence on VGS because it is proportional to the square of VGS minus VTN. As VGS continues to increase, VOV also increases. When VOV becomes greater than VDS, the device moves into the triode region, where ID becomes approximately linear with VGS. So in the ID versus VGS curve, an NMOS device goes from cutoff to saturation and then to triode. This idea will appear again when we discuss MOSFET amplifiers. When an N-MOSFET operates in saturation and VDS keeps increasing, the potential near the drain also increases. As a result, the pinch-off point moves slightly away from the drain and toward the source. The pinch-off point is where the channel voltage equals VDS sat, which is equal to VOV. As VDS increases, an additional depletion region length, delta L, appears between the pinch-off point and the drain. The voltage across this short region is delta VDS equals VDS minus VDS sat. A larger VDS gives a larger delta VDS and a larger delta L. It may look as if the channel is broken, but electrons that reach the pinch-off point can still be swept into the drain. Because delta L is very short, the lateral electric field in this region is very large, so it strongly pulls electrons into the drain and forms the drain current ID. Therefore, the channel current is still mainly determined by the triangular inversion charge distribution, but the effective channel length is reduced from L to L minus delta L. This phenomenon is called channel length modulation. Since the channel current ID is inversely proportional to the inversion channel length modulation increases the current by shortening the effective channel from L to L minus delta L. Therefore, ID can be written as 1/2 mu n C oxide W over L minus delta L times VOV squared. This can also be rewritten as 1/2 mu n C oxide W over L times the quantity 1 minus delta L over L raised to the negative 1 power times VOV squared. Because delta L is much smaller than L, we can use the binomial approximation. The term 1 minus delta L over L raised to the negative 1 power is approximately 1 plus delta L over L. Therefore, ID is approximately 1/2 mu n C oxide W over L times the quantity 1 plus delta L over L times VOV squared. The length change delta L is a function of VDS, so we write delta L equals lambda prime times VDS. Here lambda prime is also a process-dependent parameter determined by the VLSI technology. Substituting this into the current equation gives ID equals 1/2 mu n C oxide W over L times the quantity 1 plus lambda prime VDS over L times VOV squared. If we define lambda as lambda prime over L, then ID becomes 1/2 mu oxide W over L times VOV squared multiplied by the quantity 1 plus lambda VDS. This shows that even in saturation, ID still increases slightly as VDS increases, as shown by the positive slope in the saturation region of the ID versus VDS curve. If we extrapolate the straight line portion of the saturation region ID versus VDS curves back to the VDS axis, the curves intercept the axis at -1 over lambda. This behavior is similar to the early effect in BJT devices. Therefore, channel length modulation in a MOSFET is often called the MOSFET early effect. The value 1 over lambda is defined as the MOSFET early voltage, VA. VA is positive and has units of volts. Because VA depends on both the channel length L and the process technology, it can be written as VA equals VA prime times L. Here, VA prime is determined by the process and is independent of L, with units of volts per micrometer. This means the circuit designer can choose the channel length to affect VA. Since VA is proportional to L, a shorter channel gives a smaller VA and stronger channel length modulation. In contrast, a long channel device has a large VA, so the channel length modulation effect is much weaker. From the ID versus VDS curve, the slope in the saturation region is defined as the reciprocal of the output resistance, RO. Therefore, the MOSFET output resistance RO is the reciprocal of the derivative of ID with respect to VDS in saturation. Substituting the current equation gives RO equals the inverse of 1/2 mu n C oxide W over L times VOV squared times lambda. This is equal to 1 over lambda ID, or VA over ID, where ID is the drain current without channel length modulation. The total drain current of the MOSFET can be written as the drain current without the VA effect, ID, multiplied by the quantity 1 plus lambda VDS. This is the same as ID plus the additional current delta ID caused by the VA effect. From the small signal viewpoint, delta ID can be approximated as VDS over RO. Therefore, the total ID can be modeled as ID plus VDS over RO. This equation tells us that the MOSFET drain current can be modeled as an ideal drain current ID without the VA effect, in parallel with an output resistance RO that represents the VA effect. The total drain current is the ideal current plus the extra current through RO. At the gate terminal, the oxide insulation prevents conduction current, so IG equals 0, and the gate is an open circuit. Therefore, the input resistance Ri is ideally infinite. For an ideal long-channel MOSFET, VA is infinite and RO is also infinite. For short-channel devices, however, RO is finite. Thus, RO is the output resistance of the MOSFET. This means that a MOSFET operating in saturation no longer behaves like an ideal current source with infinite output resistance. As shown in the lower right figure, when VOV increases, the drain current becomes larger and the slope of the saturation region curve becomes larger, which means RO becomes smaller. Since RO equals VA over ID, RO is inversely proportional to ID. After discussing enhancement type NMOS characteristics, we now examine enhancement type PMOS devices. For a PMOSFET, a hole inversion channel is induced only when VGS is more negative than the threshold voltage VTP. Both VGS and VTP are negative values, so the channel condition is VGS less than VTP. Because negative number comparisons can be confusing, we often use the positive voltage VSG instead. In PMOS operation, the source is usually the highest potential terminal and is used as the reference. Since VGS and VDS are negative, the corresponding VSG and VSD values are positive. When a negative drain-to-source voltage is applied to a PMOSFET, the triode region condition can be written in the negative voltage form as VGD less than VTP, or VDS greater than VGS minus VTP. This means the whole channel near the drain has not been pinched off. The oxide voltage near the drain is still more negative than VTP, so the channel remains continuous. To avoid confusion with negative signs, we can rewrite the condition using positive quantities. VDG greater than the absolute value of VTP, or VSD less than VSG minus absolute VTP, which is absolute VOV. This makes the PMOS criteria look similar to the NMOS criteria, with VGS replaced by VSG, VDS replaced by VSD, and VTN replaced by the absolute value of VTP. The PMOS triode region current can first be written using the negative quantities VGS, VTP, and VDS. Here, Kp prime equals mu p C oxide, and the hole mobility mu p is typically about 0.25 to 0.5 times the electron mobility mu n. To make the formula easier to use, we rewrite it with positive quantities. ID equals Kp prime W over L times the quantity, VSG minus absolute VTP times VSD minus 1/2 VSD squared. To operate in saturation, the condition becomes VSD greater than VSG minus absolute VTP, so the whole channel is pinched off. In the saturation region of a P MOSFET, the condition can be expressed as VDG less than absolute VTP, or equivalently VSD greater than VSG minus absolute VTP. The saturation current is ID equals 1/2 Kp prime W over L times the square of VSG minus absolute VTP. If channel length modulation is included, the current is multiplied by the factor 1 plus lambda VSD. In this expression, VSG, absolute VTP, and VSD are all treated as positive quantities. We can summarize the PMOS current voltage characteristics as shown. When VSG is less than the absolute value of VTP, the hole inversion channel is not formed, so the device is in cutoff and ID equals 0. When VSG is greater than absolute VTP, if VSD is less than absolute VOV, or VDG is greater than absolute VTP, the device is in the triode region and the channel is continuous. The triode current is ID equals mu p C oxide W over L times the quantity, VSG minus absolute VTP times VSD minus 1/2 VSD squared. When VSD is greater than absolute VOV or VDG is less than absolute VTP, the channel is pinched off and the device enters saturation. The saturation current is 1/2 mu p C oxide W over L times absolute VOV squared, or 1/2 mu p C oxide W over L times the square of VSG minus absolute VTP. In the PMOS triode region, if VSD is much smaller than 2 times absolute VOV, the drain current can be approximated as ID equals mu p C oxide W over L times absolute VOV times VSD. Under this small VSD condition, the device behaves like a resistor RDS. The resistance RDS is the inverse of GDS, or VSD over ID, and equals the inverse of mu p C oxide W over L times the quantity VSG minus absolute VTP. After discussing MOSFET current voltage characteristics, we now introduce the body effect. In many circuits, the body terminal is shorted to the source, so the source body PN junction has zero bias. However, in integrated circuits, the body of an NMOS device may be connected to the most negative supply, and the body of a PMOS device may be connected to the most positive supply. Then, the source body junction becomes reverse biased. The depletion region widens, and the threshold voltage magnitude increases. For an NMOS device, VTN equals VTN0 plus gamma times the quantity, square root of 2 phi f plus VSB minus square root of 2 phi f. Here, VTN0 is the threshold voltage when VSB equals 0, 2 phi f is related to the channel doping concentration, and gamma is the body factor. In this course, the key idea is that when VSB is not 0, the threshold voltage changes. If VSB creates reverse bias, the magnitude of VT increases, so for the same VGS and VDS, the drain current ID decreases. Next, we introduce the temperature effect in MOSFET devices. From the current equations, we can see that the drain current in both the triode and saturation regions depends strongly on carrier mobility and threshold voltage. As temperature increases, the threshold voltage usually decreases by about 2 millivolts per degree Celsius, which tends to increase ID. However, carrier mobility is also a strong function of temperature. As temperature rises, channel mobility decreases, and this mobility degradation usually dominates the threshold voltage effect. Therefore, the overall drain current decreases at higher temperature. This is why an overheated electronic product may perform worse. The MOSFET current decreases, slowing down circuit operation. Now we discuss MOSFET breakdown mechanisms. When a MOSFET operates in saturation, the channel near the drain is pinched off. In the short delta L region, the lateral electric field is very strong. As the drain voltage increases, this field gives moving carriers more kinetic energy. These energetic carriers can collide with atoms in the semiconductor, break bonds, and generate electron-hole pairs by impact ionization. The newly generated carriers are also accelerated and can create more ionization events, so the number of carriers reaching the drain increases rapidly. This is avalanche breakdown, similar to the avalanche breakdown of a reverse-biased p-n junction. Because impact ionization damages the atomic structure, this type of breakdown causes permanent damage. Another drain voltage-related breakdown mechanism is punch-through, which mainly occurs in short-channel MOSFET devices. The reason is that the depletion regions of the source body and drain body p-n junctions are close to each other in a short-channel device. As the drain voltage increases, the drain side depletion region expands. Eventually, the source and drain depletion regions connect under the channel, creating a leakage path below the channel and causing the drain current to rise sharply. This is called punch-through. Since it does not necessarily involve structural damage, punch-through is usually not a permanent breakdown mechanism. Besides avalanche breakdown and punch-through, another breakdown mechanism is oxide breakdown. As VLSI technology advances, the gate oxide becomes thinner, so the electric field across the oxide becomes stronger. Also, the VGS voltage is usually larger than the VGD voltage, so the oxide field near the source side can be especially strong. If the gate voltage is too high and the oxide electric field reaches the dielectric breakdown limit, the oxide structure is damaged and no longer provides good insulation. This produces a large gate leakage current. To prevent this, input protection devices are used to limit the gate voltage so that it does not exceed the maximum voltage the oxide can withstand. At the end of this video, we introduced depletion-type MOSFET devices. The devices we discussed earlier are enhancement-type MOSFET devices. A depletion-type MOSFET means that a channel already exists when all terminals are grounded. This is usually done by physically implanting dopants in the channel region. In other words, a depletion-type N MOSFET has a negative VTN. To turn off the device, a negative VGS must be applied to deplete the electrons in the channel, as shown in the figure. For a depletion-type P MOSFET, VTP is positive. This concludes our introduction to the characteristics of MOSFET devices. Please look forward to the next section. See you next time. Bye-bye.